In this video, we're going to share with you guys what does it mean for something to be a solution to an equation or to a system of equations. So we've got this equation here, y equals -3/2 x plus 13/2. And we want to see, is the point -2, 5 is a solution to this equation. Remember, for something to be a solution to an equation, it means algebraically that it makes the equation true. I can swap out my x and y here for my x and y up here and see if the equation is true. So y, I'm going to swap out for 5. Does 5 equal -3/2 times my x value, -2, plus 13/2? Okay, if I simplify this other side, -3 times -2 over 2 is the same as +6/2, which is +3, plus 13/2. 13/2 is the same as 6.5. And so, no, 5 does not equal 9.5. And so I know that this point is not a solution to this equation. What if we were to graph it? I'm just going to do a rough sketch. We know that this is a positive y-intercept. If we were to sketch this line here, we know that 13/2 is about 6.5. And then if I plot my point -2, 5, I can see that this point is not going to be on my line. It's not a solution. It does not make the equation true. And graphically, the point is not on the line. Okay, now let's turn this into a system of equations. So a system of equations means I have more than one equation. So I'm going to throw in another equation. All right, so now we have our system of equations. Usually you'll see like a little curly brace wrapping both equations on it, saying that they are grouped together. So this and this make up our system of equations. We are given the point 5, -1, and we want to see, is this a solution to the equation? Again, I'm going to plug in x and y, and I have to do it for both equations because I want to make sure it's true for the first one and for the second one. So let's plug into the first equation, the top one. So we got y, we'll swap out for -1, it's -3/2 times x, which is 5 plus 13/2. Okay, and is this true? -1 is equal 5 times -3, or 5 over 1. 5 times -3 is -15/2. Leave that, -15/2 plus 13/2. I can combine these together since they have common denominators. So -15 plus 13 is -2/2. And -2/2 is the same thing as -1. So I know that this is true. All right, so this point is a solution for the first equation, but will it be a solution for the second equation? Let's try it out. So we got 3.5 equals 1/2, and instead of x, I'm going to swap it out for 5, minus y, or minus -1. Let's simplify. So we got 3.5 equals 5 times 1/2 is the same as 2.5, and then subtracting a -1 is the same as adding 1. So we got 3.5. We're wondering, is this true? And yes, it is true. 3.5 equals 3.5. So because 5, -1 works for the first equation and the second equation, we know it is a solution to this system of equations. What if we were to graph this? So we just graphed this on Desmos, and here we can see our two equations graphed here, and we see that 5, -1 is where the graphs intersect. And so we know that for it to be a solution graphically is where the lines intersect. That is the solution to both equations. Which is kind of cool when you think about it with all the numbers out there, all on the real number system. Only 5 as x and -1 as y will make both equations true. And other than that, no other numbers will ever make both of them true at the same time.
All right, so on your derivative assignment, there is going to be a couple of questions that ask you to graph a couple of lines and then figure out what the solution to those lines are or where those two lines intersect. Non-derivative, it's really nice because you can just move the points around and drag the lines to create the line that comes from the equation. So let's practice graphing these ones. So if we look at the first one, we know that the y-intercept is -1 and the slope is 3. So I'm going to put a point at -1 and I'm going to go up 3, 1, 2, 3 over 1, put a point there. And so now that I have 2 points, I can connect them. Now we're going to try graphing this one. We know that our y-intercept is 4 and our slope is now a -2. So we'll put a dot at +4 and go down 2 over 1, down 2 over 1. And so now this is the line for this second equation. And so easily by looking at this graph, we can see, oh, our two lines intersect at this point right here, which is over 1 up 2. So without having to solve these algebraically, I can see looking at the graph 1, 2 is the solution to these lines because it is where these lines intersect.
All right, sometimes we're just given a graph and we need to figure out what is the solution to the graph or to the system of equations. So I got this line up here graphed, and I also have this line over here graphed. I notice that these lines are parallel. They have the same slope. They will never run into each other. And remember, one of our definitions of a solution is where the lines intersect. Will parallel lines ever intersect? Nope. Oop, that's like the whole definition of parallel, right? So because these lines are parallel, they have the same slope, we will say that there is no solution. In derivative, we have to write the word none to show that there is no solution. All right, so now we have this system of equations. We got y equals negative 3 halves x plus 3, and also 2y plus 3x equals 6. And this is what it looks like with the system of equations graphed. And it looks like they are the same line, right? I don't see another line on here, and so this tells me that these are equivalent. All right, that means any point on the line will be a solution for either one. Let's verify this. If I practice solving for a variable, I can show that these are the same equations. So let's rewrite this in terms of y. So we got 2y plus 3x equals 6. I tell my story of y. Y is being multiplied by 2, and then it's being added by 3x. So if I'm going backwards, minus 3x on both sides. I got 2y equals 6 minus 3x. And then to undo times 2, I'm going to divide by 2 on both sides. I got y equals 6 divided by 2 is 3, and negative 3 divided by 2 is negative 3 halves x. So I can see that this is indeed the same equation as this. Negative 3 over 2x plus 3 is the same as y equals 3 minus 3 halves x. Okay, you can rewrite this, you can rearrange it the other way. We see that these are the same equation, and because of that, it is the same line. So when we graph it, any point on the line will be a solution. So all solutions, any xy pair that is on this line will be a solution to this system of equations since they are the same line. If I had something like this where it's 5, 10, I know that this will not work because it's not on the line. But any xy coordinate pair that's on this line will work, which is infinitely many.
Now I'm given this system of equations. We have y equals 1/2 x and y equals negative 2x minus 30. And I want to figure out where do these lines intersect, or what is the solution. I don't want to graph this because I don't want to graph a y-intercept of negative 30 because I'd have to make my graph really big. So instead of graphing this, we're going to solve this algebraically. So if we know that both of these equations are equal to y, we have y equals 1/2 x and y equals negative 2x minus 30, that tells us that if they're both equal to y, they're both equal to each other. And this is called the equal values method. The equal values method says if they're both equal to the same thing, that means that they are equal to each other. So instead of having two separate equations, I can write this as one equation. I can say 1/2 x equals negative 2x minus 30. And now I have an equation that I can solve. My first step that I want to do is I want to get my x's on the same side. So I have a negative 2x over here. So if I add 2x to this side, this becomes 0, which is what I want. So then I'll add 2x to this side. So 2x plus 1/2 x is going to give me 2.5x, or 2 1/2. And this equals negative 30. Okay, now I can solve for x by doing the opposite of multiplying by 2.5, which is dividing by 2.5 on both sides. 2.5 divided by 2.5 is 1. And so I'm left with just x on this side. So I have x equals negative 30 divided by 2.5 is negative 12. So I know that when x equals negative 12, these two lines will intersect. But now I want to figure out what is the y value when these two lines intersect. I know that x is equal to negative 12. How can I figure out what y is equal to? Well, I can just take this x value and plug it into either of these equations because I know that this negative 12 is going to make both of these equations true. It doesn't matter which equation I plug it into. So I'm going to pick the first one because it has less numbers. It's easier to manipulate. I'm going to take this first equation, y equals 1/2, and instead of times x, I'm going to say times negative 12. So 1/2 times negative 12, or we can say negative 12 divided by 2 equals negative 6. So y equals negative 6. So I know that these two lines intersect at the point negative 12, negative 6. If I were to graph this, this is where the two lines would intersect. And it's really important after we find the solution to double check that this actually works. So I'm going to take this second equation here and I'm going to plug in these values and make sure that it's true. So if I have negative 6 equals negative 2 times negative 12 minus 30, I want to know, is this true? Does this point make this equation true? We have negative 6 equals, well, negative 2 times negative 12 is going to give me positive 24 minus 30. Yes, indeed, gives me negative 6. So I know that this is the solution to this system of equations, meaning it's the point that makes both of these true, and it's where they would intersect if we graphed them.
We have another system of equations here, and let's try using the equal values method to help us solve for it. Right off the bat, I notice that they are not equal to each other, right? I got 2y minus 7x equals 6, and then I have y equals 7/2 x plus 3. Then I have to rewrite this equation in terms of y so that they are both equal to y, and therefore I can set them equal to each other. So coming down here, we got 2y minus 7x equals 6. Let's tell the story of y. Y is being multiplied by 2, and then it's being subtracted by 7x. So to undo this equation, equation, I can go backwards. So to undo minus 7x, I'm going to plus 7x on both sides. Now we got 2y equals 6 plus 7x. Okay, to undo a times by 2, I'm going to divide by 2. And remember, I'm dividing this whole side by 2. I have to divide this whole side by 2. So now we have y equals, and I can divide each piece. 6 divided by 2 is 3, and 7 divided by 2 is 7 halves, 7 over 2x. All right, now that I have this equation, rewrite it down here. Still my bottom equation here. If I do my equal values method, I'm going to set them equal to each other. So y equals this, y equals this. So that means that this has to equal this. So we got 3 plus 7 halves x equals 7 halves x plus 3. All right, if I were to solve for this, I could subtract 3 on both sides. That's the same thing. I could also get rid of the 7 halves x because that's the same thing on both sides. So we are left with 0 equals 0, which is a true equation. We can notice back up here when we rewrote it that these equations are the same. So when they're the same, that means they are two lines that are right on top of each other, and that tells me that all solutions are possible. Any point that's on this line will be a solution to the equation. There's an infinite number of them. So if you ever go through this process and you end up with something equals something and is a true equation, then you know that it's all solutions. If you ended up with something like 5 equals 0 or something, that is not true, and we know that this would be no solution because that is not a true statement. So if we were to graph it, we would know that the lines would be parallel or something like that because they don't intersect, and so there would be no solution. So if it's equal to each other, it's a true equation, then it's all solutions. If you get an incorrect statement, then you know it's no solution.
All right, so this is the last example we're going to show for this video, and it's going to talk about one more way that we can solve a system of equations, and it is by substitution. So if we look at this system of equation right here, we have y equals 3x plus 4 and 3y plus 4x equals 12. And so what we could do is we could do what Tiana did in the last example, and we could rearrange this bottom equation to be equal to y so that we could then set these both equal to each other. But that takes a lot of work to have to rewrite this and rearrange it to be equal to y and then set them equal to each other and then solve it. But if we use this substitution method, it allows us to solve this without rewriting this bottom equation. If we notice this first equation, it says y equals 3x plus 4. So that means that y is the same thing as 3x plus 4. So in my bottom equation, instead of saying 3 times y, I'm just going to say 3 times 3x plus 4 because y is equal to 3x plus 4. I'm going to rewrite this down here. I'll have 3, and then instead of times y, it's going to be times 3x plus 4. And I'm going to write this in parentheses because the 3 has to be multiplied by this entire piece. Okay, and then I'll finish filling out the rest of this equation. Now I already have it in an equation that I can solve. First thing I want to do is I want to use the distributive property, which allows me to get rid of this parentheses. So I'm going to say 3 times 3x and 3 times 4. So 3 times 3x gives me 9x, and 3 times 4 gives me 12, plus 4x equals 12. So now I'm going to combine the terms that I can that's on this side of the equation. I have a 9x and a 4x. So if I add those together, I get 13x, and then I still have this plus 12 equals 12. So now if I tell the story of x, start with x all by itself, and then I multiply by 13, and then I add 12. So if I work backwards, I'll come to this step. Instead of adding 12, I'll subtract 12 from both sides. So 12 minus 12 is 0, and I also get 0 on this side of the equation too. That's okay. So now I'm left with 13x on this side of my equation. 13x equals 0. And so I'll come to this step right here where I'm going to divide both sides by 13. This becomes a 1, so I'm just left with x, and 0 divided by 13 is just x equals 0. Now that I know my x value that makes this system of equations true, I'm going to plug it back in to solve for what the y value is. So I'm going to just take the top equation, and we'll say y equals, and then everywhere that there is an x, I'm just going to replace it with a 0. So y equals 3 times 0 plus 4. So 3 times 0 is 0. Cross that out, and I'm left with y equals 4. Now I know that my x value is 0 and my y value is 4. So this is the point where these two lines would intersect. It's the point that if we plugged them in would make both of these true. So it is the solution to this system of equations.